Yesterday, I discovered some notes on gravity I had made some time back. I thought it was before the magnetic experience. It was after when I realized something. But there was so much canceling out. But I can now tell you what I wanted to, what I am going to put formally soon. See, in 2016, LIGO, Caltech, it's an institution, it's an American institution, discovered that there are gravity waves. And there was a whole big thing about it, Not that it's more important than discovering an electron, or more important than discovering that photons are particles. But this is a big thing, So now it's confirmed that gravity is a wave. With our experiences from magnetism, how are we to translate this to ask, is it a particle as well? From other scientists besides LIGO, we know that gravity is not equal around the Earth. There are slight differences, So that is the Earth. These dark patches represent higher gravity than other places, Not all the gravity is the same, you understand? Not all of it is the same. So that's how the gravity, it's not all the same on Earth. There are different places with higher gravity. This is a geographical reality. Now, these guys at LIGO, you can use a search engine, just search engine LIGO gravity waves, they'll tell you what's going on. Now, these guys at LIGO have told us that gravity is a wave. Now, if it is true, then this experiment absolutely makes sense, and that there are differences of gravity on the Earth. So, let us make it simple. Let's try this, and this. So we have an Earth here. Everywhere gravity is the same. But we have this one dark spot which has high gravity, and this one spot which has lower gravity than the average. So this is what we should get. So this would make sense. This is our gravity. And this is the wave that should come out with. It's a wave, remember. Without any disturbance, it should keep this shape. So we can come, the Earth's atmosphere goes 10,000 kilometers. So we can come another one. Let's say this is 200 kilometers away. The wave should keep, because it's a wave, this should be kept. Even no matter how minute the differences are, we can go up to the Planck scales. These differences in gravity should remain because it has been confirmed it is a wave, and this is 200 kilometers. Then we could go up to, we can go. Let's say this is 400 kilometers. This is 1,000 kilometers. 200 kilometers, 400 kilometers, 1,000 kilometers. And this is, what shall we say this is? 50 kilometers. It's the same. You understand? If it is now, it's a wave. It's confirmed it's a wave. But does this wave organize? Are these Planck differences the same all the way? Are these Planck differences the same all the way? If they change and say they're all the same here, it is a particle. It is organized. You understand? So we can, okay, it's expensive. This is the problem with this. And it's better, it's way better that I concentrated on getting those equations for the beginning, you know. It was something fruitful and doing, because here now, what we'll need to go 50 kilometers up. Go around, have a satellite here, have a satellite here, satellite here, satellite here, satellite here, because this is all the same distance, but there should be Planck levels of differences must remain, or those differences must remain. So if I drop something here, and here, and here, those differences must remain in the pool of gravity. And if I got 200 kilometers up and put some satellites, now Khumalo doesn't have these hundreds of millions. Then I go 200 kilometers up and put satellites. It should be this. Those minute differences must stay, or it is organizing. And if it is organizing, if it's a particle, then I go 400 kilometers up. Then I go 1,000 kilometers up. And 1,000 kilometers, the nice thing, let's say 1,000 kilometers, we can test from here to 500 kilometers. Here to 500 kilometers. We can see the difference. You can use Galileo's trick and push the thing down. Those differences must remain, or it is organized into a wave. And what we have is this situation. You understand? It is organized and it's all even around. It has evened around into an oval, or smoothened out, should I say. Okay, my drawings are bad, but we're physicists here, so let's not be pretending. These should be smooth as compared to something with a bump like that, you know what I mean? So you understand. So that's how simple it is. You know? I mean, even the space station, passing, it can test the gravity here and test the gravity here. And if there's a difference between here and it's evening out, then we have a graviton. And that's it. We will formalize it and write it out sometime, year, 2 years. But that is us. That is the proof of a graviton and a way to prove it. That is if LIGO is correct. Only if LIGO is correct can we do this. If LIGO is incorrect, this experiment is worth nothing. You understand? So that's that. So there's nothing to it. There's nothing to it. It's a couple of thinking. You cancel out things, put them back in. You'll end up with it. Thank you very much. And it's called the graviton because people have been looking for it for so long. Well, there you are.